Hi. Let me see if there are any early birds here. Oh, there are these people watching, right? Both in WeChat and in YouTube. Hello. Right. Thanks for being punctual and even early. Right. We'll be starting our sample for walkthrough in 2 minutes. Okay. In the meantime, just a reminder, if you have not registered for TASMO 2025 yet, okay, please do so. We are ending our registration in 12 days. Right. So while you still receive this reminder, right, please go ahead and register if you haven't. Okay. Hello, hello. Okay, so yeah, we'll be starting in around 2 minutes. Okay, so just sit tight, get your paper and your stationery ready. All right, and yeah, we shall start soon. All right, hi everyone. We are having a 1 minute standby. Okay, until we start as usual at 5:30. Okay, someone say I'm eating. Hey, okay, please. Okay, focus while you eat. Okay, then later you can join back and listen to me, right? So yeah, we shall start at 5:30 sharp. Okay, hopefully everyone has done the paper. And this paper is taken from 2024 real paper. Mm, And yeah, I'll go through some challenging problems from there. All right, it's already 5:30, so let's get started. Okay, first of all, welcome everyone again to our P2 TASMO sample paper 4 live stream. It's the fourth time we are meeting each other. And yeah, just a reminder, if you haven't registered for P2 TASMO, right, please do so, right? Registration is closing at August 31st. And also, not sure if you are aware of it, but we are having a team category in this year's TASMO, right? This is something new. You can invite your friends to form a team of 3 to join, right? Any of your friends, as long as they are interested in math and they are willing to try out the competition, right? Just one thing to take note though, you must have at most one elite student per team. You can have one or you can have none. It's fine, right? At most one, 0 or 1. Okay, and the team category and the individual category is all based on one single paper, right? So by just taking one test, you can win both the individual prize and also stand a chance to win extra prizes from the team category, right? We have already witnessed 8 new friendships being bonded by this team category. Hopefully, we can see more people getting to know each other, making new friends with each other, right? Through this team category of TASMO, right? Again, the deadline is also by 31st August 2025. So let's say you have any students, right, in school, that any classmates in school that have not known TASMO yet and you think that he or she is interested, feel free to invite them to join together in this year's TASMO. All right, I look forward to see more friendships. And without further ado, this is sample paper 4's analysis. Right, it is taken from 2024's real TASMO P2 paper. Okay, and again, thank you so much to these kids as well as some that I might have not noted in time, right? Thank you for submitting your answers so that we can curate a targeted live stream for today, right? Hello, everybody in the chat. Okay, so with that, right, let me just give a quick analysis in sample paper 4, right? Seems like there are some equally challenging questions in section A and section B, and I see some familiar friends over here, right? Some topics we have gone through it before, but seems like it's still a bit challenging. So I will go through them today, right? So we have counting 2D shapes, right? Addition and multiplication principles, defining operations. All of these, right, are seen before, right? By the way, question 10, I don't think it's worst case scenario. I think it's something else, right? I'll talk about it. Oh yeah, it's worst case scenario, right? Sorry for the fumble up. But yeah, without further ado, right, these are the questions that I will go through today. Right, someone in the chat said TASMO is at 31st August or 15th September. TASMO, the real date is 13th September. For P2, it is 9 a.m. to 10:30 a.m. But registration closes at August, right? But the exam date is 13th September during your school holidays. Okay, hopefully this is clear enough. And yeah, with that, let's get started with section A. Right, section A, question 1 is on counting 2D shapes. Right, remember last week I've taught you how to count triangles, right? So this week we are looking at how to count squares instead, right? How many squares are there in the following figure? So when it comes to counting squares, squares has a very useful characteristic in which all of its sides are equal, right? It has 4 sides, all of its sides are equal. The strategy when it comes to counting squares is to always list in terms of size and direction, right? Why do I say direction? I'll talk about it later, right? Usually the simpler type of questions will include some upright squares of different sizes, right? As you can see over here, we usually start from the smallest size, right? This upright unit square, right, which is formed by one small square. How many of them do you see in the picture, right? Someone said Q24 is hard. Why not Q22? Oh, okay. If you need it, I can go through with you later if we have time. Okay, so here you see that we have how many 1 unit small squares here? We have 1, 2, 3, like 3 rows, 3 columns. So we know that there are 9 such upright smallest squares, right? But don't just stop there. There might be some bigger squares as well, as you can see over here. When I combine 4 small squares, I can make a 2-unit square where the length and the width are both 2 units. How many of them do you see in this picture? Right. Yes, you see 1. Let me draw them up. 1. Okay, and then you have 2, right? Just beside it, you combine some squares. 3. Okay, let me outline it a bit more obviously. And finally, 4. Over here, right? So there are 4 such squares. But don't stop there, right? Go even bigger. How many 3-unit squares are there, right? The length and the width are both 3 units. Very obvious, right? There's only 1 such big square, which is the entire square actually, right? So that is 1 such square. Okay, now some of you might think, okay, teacher, I stop here. Yeah, I only have 14 squares. No, because when it comes to counting squares, right, sometimes the question will give you some slanted squares like this, right? It's just an upright square, but rotated, tilted a bit. You will also need to count how many there are in this figure. So how many slanted 1-unit squares are there? Oh, okay. So how many slanted 1-unit squares are there? You can see that there are already some shaded squares, right? The shaded squares are over here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 such slanted squares. But also, there are some that is hidden in this blank white part, right? Let me use a more obvious color. You see there's one more here. There's another here. There's another here. There's another here. Right, so 9 shaded ones plus 1, 2, 3, 4. 4 more smallest upright, smallest tilted squares. Right, so there are 13 smallest tilted squares that you can see in this figure. And then some people will say, okay, I'll just stop here, right? 9 plus 4 plus 1 plus 13. That's my answer, 27. Right? I see a lot of your submissions just stop at 27. But please take note, we should also go larger. Right? For example, if I tilt a 2-unit square and make it slanted like this, are you able to find any of them in the picture? Right, are you able to? Oh, someone already said there are 4 such squares. Very good. Yes, so there is 1, right, as you can see over here. Then there's 2. Okay, and then don't forget up and down, top and bottom. 3, right? And then let me use a different color. 3, and then 4. Right, so for this type of slanted 2-unit squares, there is 4 of them. right? There is 4 of them. And then also, there is a 3-unit large square that is tilted, right? So you can also take a look at how many there are, right? Since it's bigger, definitely it's going to be less, right? There is actually only one such 3-unit tilted square, as you can see on the figure. So I have one such square over here, right? So with that, let's take a look at how many squares are there in total, right? When you realize that you can't go bigger, then okay, you can just count the total now. So looking at the upright squares, there are 9 plus 4 plus 1, right? And then the slanted squares plus 13 plus 4 plus 1. That will be equal to, now you can calculate with some tips and tricks, right? 9 plus 1 is 10, right? 13 plus 4 is 17. 10 plus 17 plus 1 is 28, but don't forget the little 4 here, right? So it is 32 squares, right? Altogether, I have 32 squares. So my answer is 8, right? So with that, this is how we solve this counting 2D shapes problem. And without further ado, let's move on to the next part, right? Hey, this slide is super familiar. I have taught you something like this in sample paper 1, right? But when you see this in sample paper 4, some students will still get confused. So let me just highlight the important word here, right? The important word here is discover. Let's say I have 3 keys and 3 chests. How many tries do we need at most to discover the key to each chest? Right, so let's start from the first chest on the left. At most, how many tries do I need to discover for this chest? Right, so we will try the keys one by one on the chest. So let's say I try this key onto this chest. Does it work? Well, if you're lucky, it does, right? But since we are looking for at most how many, right? Maybe you're unlucky and you will need to try again. Right. Then what about this key? You can try. And what if it works? If it works, good. If it doesn't though, that means we have already 2 fails. But do I really need to try the third key? No, I actually don't, right? Because I only need to discover the key for the chest. I don't need to open it, right? By discovering, basically it means I realize, right? I realize which key is corresponding to the chest. As long as I failed the first 2 keys, I have already identified, discovered, realized that the third key is for the first chest. So I need at most 2 tries only, right? As long as I try all but one, I can already identify which chest I should use, or rather which key I should use for the chest. Okay, let's move on to the second chest. Now that we already identified that we need 2 tries for the first chest and we found the key to it. Now, as we move on to the second chest, I have 2 keys left. Right, how many tries do I need to discover for this chest? What do you think? Right. Oh yes, so you actually don't need to try all 2 of them. As long as you try one of them, then you can discover which key corresponds to the chest already, right? If the first one succeeds, then good. If the first one fails, then the remaining key will work for this chest. So 1 try is needed to discover. And let's say, okay, this key works for the second chest. By the time we reach to the third chest, right? Do we really need to try the last key onto this chest? The remaining key, do we need to try again? We don't need, right? We can already discover, we already identify, we already realize that, yes, this key belongs to the third chest. So I don't need any new tries, right? So what do you notice? In this question, it says to discover the key to each chest. We only need to know, we don't need to open it. In that case, for each chest, the number of tries we need is just the number of keys available minus 1. Like for the first chest, if I have 3 keys, right, I will only need to try at most 2 of them to realize which key corresponds to the chest. All right, and with that, this leads to question 10 on addition and multiplication principles, as well as worst case scenario. A hotel security guard has 7 different keys for 7 rooms, right? We have 7 keys and 7 rooms. Each key can only open one specific room. The security guard has labeled which key can open which room, but the labels have fallen off. So I don't know which key is needed for which room. What is the greatest number of attempts, which is tries? How many tries does he need at most to identify the correct key for each room? Now, the question here is identify. Do I need to open the door? I don't need to open the door, right? When it comes to identify or discover, you just need to know which key corresponds to which door. We don't need to open the doors, right? So in this case, we have 7 keys, 7 doors. By starting from the first door, do I need to try all 7 keys to open the door? Right. Someone said, I am a bit confused. Now, here you are identifying the key to the room. You don't need to open it. So, for example, for the first door, right, 1 key I tried, 2 keys, 3 keys, 4 keys, 5 keys, oops, 5 keys, 6 keys I've tried. If I tried out all the 6 keys already and I still fail, I will automatically identify, I will automatically know that the last key corresponds to the first room. So I don't need to try again. I will already automatically know, I should use this key. It matches to this room. All right. So in that case, I only need to try the first 6 keys at most. So at most 6 tries are needed for this door. Likewise, after choosing the key for the first door, I have 6 keys left. Do I need to try out all 6 keys to identify the key for the second door? I don't need that, right? I can just try 5 of them. If the first 5, right, all of them fail. If someone succeeded, 1 key succeeded, good, I'll just use that key. If that key did not succeed, it's okay, right? All 5 keys have failed. That means it must be the 6th key that I will use to open the door. But I don't need to open it, right? I only need to identify. I only need to know. I only need to do the matching. I don't need to open it, right? So 5 tries are enough to know which key corresponds to the door. I don't need to open it. All right. Moving on for this door, 4 tries, right? You see each time the number decreases by 1. 4, 3, 2, 1, and 0. So altogether, we need to try out 6 plus 5 plus 4 plus 3 plus 2 plus 1 plus 0, which is 21 tries. I need at most 21 tries, okay, to identify the correct key. All right. So hopefully after this second explanation, right, since sample paper 1, you are very clear and you know when do I open, when do I identify, how do I calculate the number of tries for each such question. Okay, right. With that, let's take a look at question 11. All right. So question 11 is asking, how many distinct triangles can be drawn using 3 of the dots below as vertices? Okay, so we want to choose any 3 vertices, right? So my first question is, these are my vertices A, B, C, D, E, F. And I want to maybe, connect 3 of them to form a triangle. So this is one triangle, right? So maybe this is another triangle, right? I connect 3 points together to form a triangle. Now, in this case, the question is asking, how many distinct triangles can be drawn using 3 of the dots below as vertices? Which means my corners for the triangles must be all 3 chosen from the 6 dots. Right. So how many dots do you need to draw a triangle? Actually 3, right? For example, A, D, E, right? By choosing these 3 dots and connecting them, I can form a triangle. Right. So we need 3 dots to draw a triangle. The thing is, can I choose any 3 dots to form a triangle? Right? For those in the chat, can you tell me, right, what is an example of a triangle, or rather an example of 3 dots that cannot form a triangle? Which 3 dots cannot be used to form a triangle? Right? Some of you might say, teacher, I think I try any 3 also can. But let's say I try D, E, and F, and I connect them. Is this a triangle? Is this a triangle? This is not a triangle, right? This is just a line, right? This is just a line. So when you choose the 3 dots to form a triangle, you need to make sure you do not choose the 3 dots from the same line, right? Which means we should either choose 2 from above and 1 from below, or 1 from above, 2 from below. The key point here is, right, I must choose 3 dots such that not all of them are from the same line, right? So for example, what if I choose 2 dots above and 1 dot below, right? So now that you have decided, okay, I'm going to choose 2 dots above and 1 dot below, we now need to figure out on each row, how many ways are there to choose the dots that I want to use. So for example, here I want to choose 2 dots above. How many choices are there to choose 2 dots above? I have A, I have B, I have C. How many ways are there to choose 2 dots, right? A pair of dots from A, B, or C. Choose any 2 of them, right? C, D, E. Oh, someone said C, D, E also not correct. Can C, D, E when I draw like this. This is a triangle, right? The point is I cannot choose 3 dots from the same line, right? And to respond to some of your questions, yes, right? I can choose A and B. I can choose A and C, or I can choose B and C. So actually there are 3 choices, A, B, A, C, and B, C, to be the 2 dots above. So now that I have chosen the 2 dots above, I just need to choose 1 dot below, right? What is the number of choices? Hey, I just need to choose any one of the 3 dots. So I can choose D, I can choose E, I could choose F. Again, there are 3 choices. So then, how many triangles can I form, right? If I choose 2 dots above and 1 dot below. Now remember, addition and multiplication principles. We are choosing a pair of dots from above. There are 3 choices. And then we choose 1 dot from below, so another 3 choices. We are matching the choices above to the choices below, right? For example, A, B can match with D. A, B can match with E. A, B can match with F. So you see, any pair I choose above, I can form a triangle by matching it with any of the 3 points below, right? So AB, 3 choices. BC, 3 choices. AC, also 3 choices. So total, I have 3 times 3 equals to 9 triangles that I can form if I choose 2 dots above and 1 dot below, right? And then at this point, many students will say, okay, so my answer is A, right? But who said that you must choose 2 dots above, right? I can turn the entire picture upside down and instead choose 2 dots below and 1 dot above, right? So similarly, I need to choose 2 out of 3 dots from below. Then I need to choose 1 out of 3 dots from above. So let's first choose the pair of dots below, right? I see a little typo over here. Let me change it. 2 dots below. How many choices there are? Again, how many ways are there to choose a pair of dots from 3 possible dots? Right, we have 3 choices, right? DE, DF, or EF, right? DE, DF, or EF. Right, so yeah, so that's 3 choices. And then how many ways can we choose 1 dot above? Let me change the typo over here as well. 1 dot above. How many ways are there? Again, there are 3 choices, right? You just need to choose 1 out of the 3 dots. So A, B, C, 3 choices. So it's exactly the same as case 1, right? So according to case 1, there are 9 triangles that I can form. So in case 2, there are also 9 triangles that I can form, right? 3 times 3. I'm matching every pair below to every dot on top. So 3 times 3 equals to 9 triangles. Yeah. So in total, how many triangles can you form? There are 9 case 1. There are another 9 from case 2. Altogether, there should be 18 triangles. And so my answer is C. Right. I see that some of you have found that, oh, teacher, I just tried 1 by 1. Okay, could you go through question 7? Oh, okay. I will send, for those questions that I did not go through today, I will be sending the full solutions later after the live stream, so you can refer to that, right? These are the common challenging problems that a lot of students answered wrongly, right? That's why I'm going through here. Okay, so like I said just now, this is actually addition and multiplication principle. We need to see how to match choices above to choices below. So instead of trying 1 by 1, we start by thinking, how could we choose our 3 dots? Can we choose from the same row? Right? If we cannot, that means we should choose some from above, some from below, right? And from there, we have two cases, right? 2 above, 1 below, or 2 below, 1 above. Then for each case, we just choose the dots above and then choose the dots below. Then use multiplication principle to do this. All right, so yeah, that's how we do question 11. And without further ado, let's move on to another evil question, question 13, right? Define new operations. It seems like whenever there is a define new operations problem in the sample paper, it will appear here, right? So what is the missing number in the pattern below, right? Actually, I have 4 numbers in every pinwheel and I need to figure out, right, what is the missing number? What is the pattern? How are the 4 numbers related? And then using this pattern, we find out the missing number in the question mark here. Okay, so my advice to you, whenever you see these sort of questions, right, and you have enough time, right, start experimenting from weird numbers. I said experiment. It means we need to keep on trying, right? Keep on trying. Don't give up, right? Until you have figured out a pattern that relates to all 4 pictures given here, right? How do we relate all the 4 numbers in each of the pictures, right? For all of them. If you found one that is common for all of them, then good for you. You have found the answer. Okay. I still wonder why question 22 never goes through. Well, I will, if I have time, I will go through with you later. All right. So, okay. So now, maybe some of you might think, hey, teacher, I start from small numbers. Okay, let's start from small numbers, right? 2, 3, 9. I want to get 21. How could I get 21? Then some people might say, oh, I see 21 related to 3, right? Because 7 times 3 equals 21. Okay, so all I need to find out is how do I get 7? And then you see, oh, 2 and 9. I can do 9 minus 2, and then times 3 equals 21. Possible, right? It's possible, but can we just use one example and then just decide that's the pattern? Cannot, cannot. When it comes to this sort of define new operations, number pattern problems, we need to make sure, right, the pattern you defined applies to all the other patterns or all the other figures as well, right? So why does it not apply? That's because if you look at the next pattern, you will see something minus 19 times 5 is equal to 67. But 67 is not even a multiple of 5. So this pattern definitely is not defined by what I did just now. But it's okay, right? At least you made a good first effort. Okay, we just need to look somewhere else to search for inspiration. All right. In fact, here, other than experiment, right, which means trying, I also said we start from weird numbers, right? Which number do you think looks sus or weird or special? Right? Which number looks sus? I would say 101 looks sus because not only does it appear as a 3-digit number, it is also way bigger than all the other numbers here. And 101 is almost very close to a pretty number. Which number do you think it is? Right. Yes, it is 100, right? Or 100, right? So I have an extra one over here. 101 is very close to 100, but there's an extra one. Is there somebody that can help us clear away the extra one in the 100? That is 101 and 11. And in fact, 101 minus 11 equals 90. So now, as long as we figure out how to make 90, good, then you found the answer. Then let's see. 90. 9 and 8, how can I form 90? What do you think? How can I use 9 and 8 to form 90? Some kids might say, hey teacher, 90 is divisible by 9, right? Right, so 90 is equal to 9 times 10. So this 10, I can make it from 8 plus 2. So I can just use 9 times 8 plus 2 to help me, right? Well, possible, right? But don't forget, once you found the pattern, try it on all the others, right? To see whether it works or not. For example, I can try using the first one, right? Let's come back to the first one. 21 minus 9 is equal to 12. Right, possible. Okay, but then if I say 12 is equal to left side number, 2 times right side number 3 plus 2. Is that correct? Is that correct? No, cannot, right? So yeah, it's definitely not correct. So we cannot use this as the conclusion to our pattern, right? So, oh no, I can't form 90 using 9 times 8 plus 2. Is there another way to form 90? There actually is. Now let's look closely. We know 90 is equal to 9 times 10. Can we form 9 and 10 using another way? Well, if you look at the numbers given to you, 9 plus 1 is 10. 8 plus 1 is 9. Hey, wait, I found my 10, I found my 9. So can I just get the 9 and 10 from the numbers on the right side and the left side, each plus 1? Right, 9 comes from 8 plus 1. 10 comes from 9 plus 1. Maybe, right? Maybe I can do this. So let's take a look at the other patterns to see, does it work? So as usual, let's start from the first one. 21 minus 9 is equal to 12. Then if I do 2 plus 1 and 3 plus 1, I will get 3 and 4. And just nice, 12 is equal to 2 plus 1, which is 3 times 3 plus 1, which is 4. So it works for this pattern. It works for this pattern. But don't forget, we need to try on every one given to you to see if it works on all of them. So let's take a look at the fourth picture, the fourth pinwheel over here. Again, top number 86 minus bottom number 2. 86 minus 2 is equal to 84. If I do 6 plus 1, I will get 7. If I do 11 plus 1, I will get 12. And just nice, 6 plus 1, 7, times 11 plus 1, 12, is equal to 84. Right, which is equal to 86 minus 2. So the operation also works on the last pinwheel. Since it works on all the pinwheels given to us, that means we must have found our pattern, right? Good job, everyone. We found it together, right? But won't A, C bypass B? So won't there be already 3 dots? Adding 1 dot below. Okay. So let me finish this question and I'll go back to question 11 to answer Melody's question. Okay, so how about this? Now let's try top minus bottom. 67 minus 19 is equal to 48. All right, then we know 5 plus 1 is equal to 6. Something plus 1, so something plus 1 times 5 plus 1, something plus 1 times 5 plus 1 is equal to 48. So 5 plus 1 is 6, right? 48. Something plus 1. I want something plus 1 times 6, that is equal to 48. That means this something plus 1 must be 8. Right? But don't get too hurried and circle your answer 8. Right? This should be something plus 1 is 8. So your something should be 7. Right? So we have found our answer, C. Right? C is our answer over here. All right. Now that is how I do this question. And now let's quickly move back to question 11 to answer a concern. A good question mentioned. Okay. So somebody in the chat just said, teacher, if I connect A and C and then I connect with D, let's say, wouldn't I have already passed through 1, 2, 3, 4 points? Right. But over here, they are saying to use 3 of the dots below as vertices. That means we want our 3 dots to be the corners of the triangles. Vertices means corners. As long as I create a triangle using 3 dots as my corners, right? 1 corner, 2 corner, 3 corners, then I am fine, right? In between, in the sides, I might pass through another dot, I might not, but it doesn't matter because I want to see my corners are formed using any 3 dots, right? So the 3 dots as my corners, that is the point of this question, right? Hopefully you are understanding it better now. Okay, so with that, right, we have gone through all the questions in section A, right, some tricky ones, and let's move on to section B, right? We will start with addition and multiplication principles again, right? So for my dear CO kids, CO prep kids, right? We have learned this actually for everyone because we have actually seen this problem before, right? In at least one sample paper. How many 4-digit numbers have only even digits? Now, does that mean I'm looking for even 4-digit numbers? Is it the same as asking how many 4-digit numbers are even? No, right? 4-digit numbers, only even digits. That means each and every digit must be even, right? What are the even digits that you know? What are the even digits that you know? You know, 0, 2, 4, 6, 8. So I want to use these digits to form my 4-digit numbers. Also, did the question say that you must use each digit only once? Did the question say you cannot repeat the digits? No, right? So in this case, the question actually says that you want even digits only, but it didn't say you cannot repeat. So you can repeat, right? For example, 2, 2, 2, 2. I mean, it's a 4-digit number. It only has even digits. So this is one possible number, right? So we can repeat our digits unless the question say different digits, distinct digits cannot be repeated, right? Then you cannot repeat the digits. But in this case, it didn't mention that. So feel free to repeat your digits. So this is where a positioning method comes into play again, right? Since we want 4-digit numbers, we list out the 4 seeds for the numbers and we consider one by one, right? So what are the available even digits that we can choose from? We can use 0, 2, 4, 6, 8, right, to form the 4-digit numbers. Now, I have 5 possible digits, right? Does that mean, okay, 5 ways, 5 ways, 5 ways, 5 ways? That's all. Does that mean that is the case? In these 4 digits or 4 place values, can you tell me which one is special? Which one is special? Can I say everybody is 5, 5, 5, 5? Right. Can someone reply me? Oh, okay. Cannot, right? Why is that the case? Because, right, there are seats with a special condition. In fact, whenever you see the digit 0, you should be very alert, right? Because 0, as teacher Yong Lam likes to say, is a very sus digit. 0 cannot appear at the highest place value, which means at the thousands place, I cannot put 0, right? It must not be 0. So in the thousands place, how many ways are there for me to select an even digit? How many ways are there for me to select an even digit? That's right. 4 ways, right? It could be 2,000, 4,000, 6,000, or 8,000. Right. So this is the seed with a special condition. We always start considering from that. Then let's move on to the hundreds, right? For the hundreds, there is no restriction. I can pick any out of 0, 2, 4, 6, 8. So there are 5 ways to choose the digit for the hundreds place. Likewise, tens place, no restriction, 5 ways. Ones place, no restriction, 5 ways. So altogether, 4 times 5 times 5 times 5. Remember, we multiply all the numbers of possibilities to find the results. Because I am choosing the thousands, and then the hundreds, and then the tens, and then the ones, right? Every time we are matching the ones with the tens, with the hundreds, with the thousands, right? So we have to multiply all of them to find the result, right? What is 4 times 5 times 5 times 5? Okay, so some of you have already known, right? 5 times 5 is 25. 25 times 4 is 100, right? In fact, these tips and tricks in multiplication will help you to do your calculations very quickly. And hint, hint, one of the questions in sample paper 5 involves this trick, right? So keep a lookout for it. So then we have 100 times 5, so it's 500 4-digit numbers in total. So my answer, 500. Okay, so yeah, that's how we attend this question, right? 500 4-digit numbers. And hopefully by now, whenever you see a forming numbers type of question, you know how to do it. Okay, I trust everyone who is here, right? So with that, let's move on to the next question. Yes, it's 500. That's the answer. Okay, now let's move on to a shapes question. Right now, this question has the lowest correct answer rate. So I'll go through in more detail. So what is the perimeter of this figure? Just nice. My CO class has gone through this last week, right? So perimeter actually means, right, the total length of all the sides outside, around an enclosed figure. So for example, in this figure, we have these sides that I'm highlighting, they will comprise the perimeter of the entire figure, right? It's the total sum of the lengths around the shape. Now, one particular shape that you should know how to find the perimeter for is a rectangle, right? Because a rectangle has length and breadth, right? And the opposite sides are equal, so there are 2 copies of length, 2 copies of breadth. So the perimeter of a rectangle is length times 2 plus breadth times 2. Or to put it simply, length plus breadth times 2, right? I have one set of length and breadth. I have another set of length and breadth. So 2 sets, L plus B, length plus breadth, times 2. Okay? So this is how it looks like, right? You can have a screenshot, right, to take some notes later. And with that, let's look at this figure. The figure in the corner here, we are asking for its perimeter, but I don't think this is a rectangle, right? So how should I do this? Hey, you see, it feels like a rectangle being eaten a piece away, right? A piece of it is eaten away, right? But then remember, perimeter is about the total length of the sides. Now, what happens if I rearrange some sides? For example, I know that these sides, they make up my perimeter, right? Now, if I move this side to form like this, so these sides now come here. This side now comes here. Did I change the length of any side? Did I change the length of any side? I actually didn't, right? What I did is I just rearranged the sides. I didn't change the length. So the total length did not change. The perimeter did not change. So in this case, we formed a rectangle and we know the perimeter of the rectangle is the length is 10. So 10, okay, plus the breadth is 6. So 6 and then times 2. So that will be equal to 32 cm. Right, 32 cm. Right, good. Some of you have already answered here. So this is what we call the push-out method, right? We rearrange the sides without changing their length, right? In order to prepare for the next slide, let me change the position of my workings. Okay, now my question is the perimeter still 32 cm? In this picture, it kind of looks like a rectangle, right? Is the perimeter still 32 cm? Now remember, perimeter refers to the sum of the lengths of the sides surrounding the figure. So all of these will add up to form my perimeter. All of these add up to form my perimeter. Okay? And yeah, it kind of looks like a rectangle, right? You see, as long as I move this side down here, I removed it. It comes here. Yeah, that's my rectangle. So my perimeter must be 32 cm. Is that correct or not? Is it still 32 cm? Yeah, it's called a push-up method, correct? But is my answer 32 cm? Did I really count all the sides already? Are all the sides really pushed out to the rectangle already? No, why? Because I just shift the length and I form the rectangle. I didn't change the length, so I can still calculate the perimeter this way, and it's easier. But then, you see, I have these 2 extra lines. I didn't push them outside of the rectangle, but they still count as the perimeter of my figure. They are still part of the perimeter of the figure. I need to include them in my total length. So actually, we need to be careful for the extra sides. Other than 32, I will also need to count these 2 lengths as well. Right? How many is it? I don't know. But I also need to count their lengths here to find my actual perimeter. Okay? Why 6 is equal to 10? No, it's not. It's 10 plus 6. Okay? Right. Now, with that, 38. But hey, some people say, okay, teacher, this is 3. Now, unless there is a guiding line telling you that, okay, this is 3. This is 3. Unless it is that, right? Don't assume. right? Here, technically, I didn't give you the length, right? But sure, yeah, you can think that if it's 3, then if it tells you it's 3, use it. All right. Okay, so with that, wow, what figure is this, right? We want to find the perimeter of this figure. If rectangles with a length of 9 cm, so basically this is 9, and width of 3 cm, so this is 3, right? 9 cm, 3 cm, is arranged to form the shape shown below. What is the perimeter of the resulting shape, right? We want to find the sum of the lengths of the sides that are surrounding this figure, right? So that includes all of these staircase shape, right? All of these. What is their perimeter? Okay. Now, when it comes to perimeter, right? This is the perimeter. There is an easily mistaken point. These sides inside, right? Like what I'm drawing now, they are not part of the perimeter. The perimeter must be the sides around the figure, outside. These sides inside, they are not counted as my perimeter. So please take note of that, right? So with that, we can just use the push-up method to do this, right? You see, we know how to find the perimeter of a rectangle, but this is not a rectangle. But maybe I can rearrange the sides a bit without changing their lengths to change this figure, to rearrange them into a rectangle so that it's easier to find their perimeter. And so, yeah, if I try to trace out the rectangle, that's kind of looks like it, right? If I push out all the sides, push out as much as possible, my rectangle could look like this. Let's see how much we could push out, right? For example, you see the bottom length has been covered by my exact perimeter, but the top length, right? My sides did not cover the full rectangle yet, but it's okay. You see all these sides, I could push them out, push them out, push out. All these sides, all of these. I can push them out, push them out, push them out. All these sides, push them up, push them up, push them up. And I form exactly the entire length of the rectangle. Let me use a ruler to draw it, right? I formed exactly the entire length of the rectangle, right? It is covered. And also, if you look at the vertical sides, right, these that are outside, I can push them, push them, push them to come here. Take note, while I'm rearranging the sides, I did not change their length, right? These vertical sides, push them out, push them out, push them out, and they come here. And with that, my sides, my line segments have covered the entire perimeter of the rectangle. So now we can find the perimeter of the rectangle now, right? The length of the rectangle is formed by the length of 1, 2, 3, 4, 5, 6, 7, 8, 8 small rectangles. So the total length is 8 times 9 equals 72 cm. And likewise, the breadth of the rectangle is formed by 1, 2, 3, 4. 4 times the breadth of the rectangle. So 4 times 3 is equal to 12 cm. Okay, and then 72 plus 12. Don't forget that it's one set of the length and breadth. A rectangle has 2 sets of it, right? So I need to multiply by 2. And so that is definitely the perimeter of the rectangles, right? Definitely the perimeter of the figure. Unless there are some extra sides that you might have forgotten, right? So remember, when we use push-up method, it's very convenient. Just rearrange the sides. But after you formed the regular figure, the rectangle, you need to ask yourself, did I include all of the sides around the rectangle? Or rather, are all of the sides already pushed outside of the rectangle? Or are there some extra sides inside? Now, there is still some sides that I did not push outside to the rectangle, so they are not yet included in the calculation just now. These sides are over here, over here, over here, over here, right? These 4 pink sides, they have not been included in my calculation of perimeter yet. So I need to add them, right? The extra sides. There are 4 copies of 3 centimeters. So I will need to add them. They are extra when I calculate my perimeter. All right. So some of you have already given me, yes, this part is 168. Right, and 4 times 3 is 12. So my answer, 168 plus 12, that is equal to 180 centimeters. And that is the perimeter of this shape. Okay, so with that, that is how you get this answer. Right? Hopefully you gain a better understanding of the push-up method, which is also going to be in sample 5. Okay, so keep a lookout for that. And let's move on to question 23 on matchsticks and numbers. Now, this is also similar to what you see in sample paper 1 with a different approach. How many different 3-digit multiples of 5 can be formed using an odd number of matchsticks in total? Right, so as usual, we need to remember 2 things. Number 1, what is the value of the digit? Number 2, how many matchsticks are needed for each digit? So I have listed out the digits 0 to 9 over here. Whenever you see a matchstick problem, remember, you must note down how many matchsticks are needed for each digit. So for 0, there are 6 matchsticks. For 1, 2 matchsticks. For 2, 5 matchsticks. For 3, how many matchsticks? How many? How many are there? 5 matchsticks, right? And then 4 matchsticks for digit 4, 5 matchsticks for digit 5, 6 for digit 6, and then 7 is not 7 matchsticks, right? Don't get tricked. 1, 2, 3, 3 matchsticks. 7 matchsticks for digit 8 and 6 matchsticks for digit 9. Right, so remember, how many matchsticks do I need to form each digit? Whenever you see a matchstick problem, immediately you need to list them down. But on top of that, right, this question is not interested in how many matchsticks we need. Because remember, we want to use an odd number of matchsticks in total. So to make sure we use an odd number of matchsticks in total, we will just consider, right, each digit. Did I use an odd number of matchsticks or even number of matchsticks? Right. So this is also something you need to take note. Okay. So for example, even number of matchsticks 0, 1, even for 1, odd for 2, odd for 3. As long as you listed out how many matchsticks are needed, you just see is 6 even or odd, even 2 even or odd, 2, 5 even or odd, odd. Then you continue listing, right? Even, odd, even, odd, odd, even. And now you notice there are 5 digits that uses an even number of matchsticks. They are 0, 1, 4, 6, 9. They use an even number of matchsticks. And odd number of matchsticks, again, 5 digits. 2, 3, 5, 7, 8. They uses odd number of matchsticks. So we understood this part, right? We need to identify whether the number of matchsticks is odd or even. We also need to consider 3-digit multiples of 5. Now, this is referring to the value of the actual number. I'm not saying you are using multiples of 5 many matchsticks. I'm saying the number you form is a multiple of 5. Now, to form this number, which digit, or rather, which place value is special? For multiples of 5, what is special about these numbers? What is special about multiples of 5? Their ones place must be either 5 or 0. The ones digit must either be 5 or 0. Okay, so there are 2 cases to consider here, right? So again, let's move on to a bigger canvas, right? And recall which digits uses an odd number of matchsticks. Yeah, it is 2, 3, 5, 7, 8. Okay, and the other 0, 1, 4, 6, 9, they use even number of matchsticks. Okay, and since we are forming 3-digit multiples of 5, then the ones digit can either be 5 or 0. So let's consider case by case. What if our ones digit is a 5? Right, so ones digit is a 5, I need to use matchsticks to create 2 more digits. Now we already know that 5 uses 5 matchsticks, which means it uses an odd number of matchsticks. We want the total number of matchsticks used to be odd. So that means a something number plus a something number plus an odd number must be odd. Here comes your application of odd and even number properties, right? What kind of numbers adding together will be odd? I already have an odd number, right? Let's say I have an even number of matchsticks for the 100 sticks. Please take note, this is referring to the even number of matchsticks, odd number of matchsticks. I'm not saying whether the digit is odd or even. Okay? So even plus what plus odd is odd. I already used even number of matchsticks, odd number of matchsticks. To maintain the total number of matchsticks to be odd, the tens place must also use an even number of matchsticks. So now that we decided, okay, it could be even, or what if I used an odd number of matchsticks for the tens digit? Then can I still use an even number of matchsticks for the hundreds digit? I cannot. Right, instead I have to use an odd number of matchsticks for the hundreds digit as well. So again, odd plus odd, then my total number of matchsticks is odd as well. So now we just need to see how many digits can we form in each position. Now in the hundreds place, even matchsticks, 0, 1, 4, 6, 9. Remember which digit is sus? Right, the 0, this digit is sus because 0 cannot be at the highest place. Which means, how many different types of digits can I form for my hundreds place here? Can I use 0? I can't use 0. Right, so I could either form 1 or 4 or 6 or 9. So how many even matchsticks digits can I make at my hundreds place? Only 4. But when it comes to the tens place, I can make 0 now, right? My tens digit could be 0. So there are 5 choices. So 4 times 5 is equal to 20. All right. Now, when it comes to odd matchsticks, then this worry doesn't exist, right? Because all the digits here are non-zero. I can put them at the hundreds place. I can put them at the tens place. And I can repeat the digits. So here, 5 choices for the hundreds place, 5 choices for the tens place. 5 times 5, 25. All right. So up till now, we have found 20 plus 25, that's 45, the digit multiples of 5. But don't forget, my ones digit could be 0, right? And this time, if my ones digit is 0, it uses an even number of matchsticks. Okay, here's a little typo. It uses an even number of matchsticks. Okay, and likewise, there are again 2 cases, right? But here, 0 uses an even number of matchsticks. So, what if my hundreds place, right? I can still decide which digit to use for my hundreds place and my tens place, right? What if my hundreds place uses an even number of matchsticks? Now remember, the total number of matchsticks I use must be odd, right? I want to use an odd number of matchsticks in total. So even plus even. Right now, I have used an even number of matchsticks. To make the total number of matchsticks odd, right? Even matchsticks. Even matchsticks. So the total number of matchsticks I have now is even. But I want it to be odd. So I have one more digit left. So this digit, I can only use an odd number of matchsticks to create this digit. Right? So even plus even, it's odd. Or I can swap around, right? I could instead use an odd number of, I can instead use an odd number of matchsticks for the hundreds place and even number of matchsticks for the tens place. So now let's consider how many choices are there to form the digit at each place value. Here, again, if the hundreds place needs to be an even matchstick digit, right? If my hundreds place needs to be an even digit, then I have how many choices? It again cannot be 0, so it could only be 1, 4, 6, or 9, right? 1, 4, 6, or 9. 4 choices. But for my odd matchstick digit, there are 5 choices, right? 2, 3, 5, 7, 8. Any of them could work. So that's 20. 4 times 5 is 20. If my hundreds place is a odd matchstick digit, any of 2, 3, 5, 7, 8 can be included here. So 5. And for the tens digit, again, no restriction. So 0, 1, 4, 6, 9 could all go here. 5. So 5 times 5 is 25. Right. So for each and every case, we have considered how many numbers there are. Let's find their total. We have 20 plus 25 for case 1, plus 20 plus 25 for case 2. And that will give me 90 possible 3-digit multiples of 5 in total. All right, so altogether, I can form 90 3-digit multiples of 5. Okay, and like some of you have mentioned, odd plus odd plus odd is odd, right? So you have to remember your odd and even number properties. Okay, so let me So this is question 23. Let's move on to question 24. Right, question 24 is a vertical number puzzles question, right? In every TASMO, right? There's definitely a vertical number puzzle question, right? At least in the few years recently. Now, in the following addition, the same letter represents the same digits and different letters represent different digits, right? This is the very standard way, right? Now, what is the maximum value of the 4-digit number MATH that satisfies this condition? Okay, so we want to see MATH. What is the biggest number that it could be? Now, it seems like, wow, teacher, there's a lot of possibilities. I'm scared, right? But don't worry, right? We can still analyze to see there are some digits that have one possibility, right? For example, let's look at the thousands place. What do you think M could be? Now we know the result is 2. So could M be 3? Could M be 4? Cannot, right? It must be smaller or equal to 2. But then what if M is 2? If M is 2, but look at the answer. The answer is 2023. The hundreds is 0. To maintain that, that means my A must be 0, my T must be 0. But oh, that means this 3-digit number starts from a 0. That's impossible. So M cannot be 2, right? Otherwise, my T will be 0. A must be 0. That means the only possibility for M is 1, right? M could only be 1, right? As long as you finish your analysis, please change all the M's to 1 so that you can look further. Now, after we focused on M, right, the thousands digit, now let's look at which place value has the most info now. The most info is at the tens place, right? So first we start from the thousands place, right? Usually the highest place value gives us more info, okay? And then, right, T plus 1 is 2. Oh, I know 1 plus 1 is 2. That means T is 0, right? Again, we have just figured that T cannot be 0. Otherwise, the second number, the highest place is 0. Doesn't make sense. Then how could T plus 1 be 2? That means these 3 numbers must give me a 12 instead, right? There must be a carryover at the hundreds place, right? So for the tens, there must be a carryover at the hundreds place. So, but the T is at most 9, right? 9 plus 1 is already 11. How could I get 12? How could I? Well, that's because, right, maybe there is also a carryover on the tens place itself. That's why we have 1 plus 9 plus 1 plus 1 that is equal to 12. Right, so T could be 9. Or maybe the carryover at the tens place is 2 and T is 8. That's also possible, right? Because over here, I am adding up 3 1-digit numbers. It's possible, but that the result is 23, right? For example, 9 plus 7 plus 7 is 23, right? So it has a possibility that the carryover here is actually 2, right? So then, let's take a look. What happens if my T is 8? Then, this is 8, right? This is 8, right? And we know 1 plus, if T is 8, that means looking at the hundreds place, 1 plus A plus T, which is 8, is equal to carry over 1, definitely, right? Because there's 0 here. So there's 10. 1 plus A plus 8 is 10. Because it couldn't be 0, it has to be 10. That means A is 1, but could A be 1? Different letters represent different digits. Oops. Different letters represent different digits. My M is already 1. A cannot be 1, right? So we reject this case. So T cannot be 8, which means T must be 9, right? So we confirm that T is 9 now. And that means 9 plus 1 plus 1 is 11, right? 9 plus 1 plus 1 is 11. So there must be a carryover of 1 on top of this tens place. So 1 plus 9 plus 1 plus 1, indeed it is 12. And now we have 1 plus A plus 9 is equal to 10 at the hundreds, which means A must be what digit? A must be 0, correct, right? So A is possible to be 0. So we get this result. T is not 8, T is 9, A is 0. Yay, we found MAT, right? We just need to know what is H. Now, in the one space, does it mean that H plus C is 3? Actually not, right? We see that it's a carryover here. So H plus C is 13. But then we have a lot of choices. What H could be 1, H could be 2, etc. A lot of choices. So how do I know what value H could be? Well, that's because the question has another keyword, right? It says we want the maximum value. We want the maximum value. We already decided 1, 0, 9 as the first 3 digits at the front place values. To make this number the maximum, we need to consider H as big as possible, right? So we start from bigger values from H and work down. Now let's try one by one. Could H be 9? Cannot, right? Because it's the same as T. Could H be 8? If H is 8, then A plus C is equal to 13. But C plus C, two same numbers adding together, it must be even. It couldn't be 5, right? 8 plus 5 is 13. Cannot be 5. So H equals to 8 doesn't work. Now, if H equals to 7, 7 plus C is equal to 13. And then you know, oh, C is 3. C is 3. So then 7 plus 3 is equal to 13. And yeah, H could be 7. H could be 7. So we have found the maximum value, 1097. Right, so the maximum value might seem intimidating at first, but we always start from the breakthrough point, likely at the highest place value or the lowest place value. Okay, and then we try to assume one of the digits, and then we look at the other places with the most information to decide where to consider next. Sometimes there might be 2 cases, especially when we add 3 numbers or more, right? My carryover could be 1 or 2, right? So there might be some more cases. Just try one by one. All right. And with that, that's the end of the day, right? I've been going over time, right? I do note that there are some requests, right, for questions like 7, 22, etc. Right? I will be sending the full solutions in the WhatsApp and WeChat group later for parents' references, right? So please look at that. And if you still have any problems, feel free to raise them to me, right, privately or in the group chat, and I'm more than happy to answer your concerns. Okay, and with that, please also be reminded that we will be using an answer sheet for our TASMO 2025 exam, right? So starting from sample 5, it is a good chance for your child to be familiarized with how to use the answer sheet, right? How to shade the correct answer for MCQ, how to fill in the blanks for fill in the blank question, right? We do not request your answers to be in 4-digit format, right? If your answer is 12, just write 12. It's okay. All right. And so please practice. I'll be sending the answer sheet to the group chat shortly as well. Okay, and that's all for today. And like I mentioned, any questions, just raise them up in the group chat. Okay, or reach out to me. Okay, and yeah, later I will also be sharing sample paper 5, which is a original set of questions again, right? And we will be meeting next Tuesday for our sample paper 5 live analysis, right? So I will see you again next Tuesday as usual. All right, and that's the end of the day. Thank you so much. Okay, hope you have a wonderful evening, and I'm happy to see that everyone is improving together. All right. Thank you so much. Goodbye. That's the end of today.